Hello. Today we are going to talk about an application of the difference quotient that we've been talking about lately in class. We've got to go backwards a little bit though and do a little review of quadratic equations with projectile motion. Again, projectile motion is anytime something is launched upwards into the air, that something has an initial velocity that's could be anything, could be a rocket or a throw or a kick, but it doesn't have its own engine, so it's going to eventually slow down and come back down to ground. All right, so that formula, very much like the quadratic equation, or y equals ax squared plus bx plus c, so it's just a variation of that. It's a function of time, that's the f of t. The negative 16t squared, well, the negative 16 is the Earth's gravity, so that number would change if you were on a different planet. And then plus vt, where, again, t is the time, and v is the initial velocity. How fast was this object moving at the beginning? And then plus h, where h is the initial height. So down here at the bottom there's a little graph. Pretend that, you're shooting a firework off the top of the buildings downtown for, Three Rivers or 4th of July or something. And the rocket is being, or the firework is being launched from the top of something. That's the initial height. It didn't start at ground level. This one started off high. And it gets to its peak point, and that's where it explodes, and then the remnants fall to the ground on the people below. If that's ever happened to you. Definitely happened to me before. If you're downwind of the fireworks, you get some debris on you, because again, it does come to the ground, and it follows the parabola pattern. And then again, this is assuming that there's no wind resistance. The wind resistance could shift or alter the shape of the graph to not be quite so symmetrical. All right, so that's a little background review. And now we're going to talk about average velocity. All right, and here's the formula for average velocity. All right, V for velocity, and then little average, AVG, as a subscript. And then we got this information here. The S would be the function name, S of t. And again, it should look a lot like the difference quotient, or one of those variations of the difference quotient we looked at the other day. And then your interval would be from time 1 to time 2, whatever that happens to be. So again, you can see where the numbers are going to fill into the equation. All right, so let's do an example and see how this works. All right, so here's our example. A rocket is launched from ground level with an initial velocity of 70 feet per second. What's the average velocity from 1 second to 3 seconds? All right, so let's start off finding our function, our S of t, function related to time. And we're using S because I don't know why. Could have used F, just the formula uses S, so we'll use S. All right, now because we're on Earth, we're always going to get negative 16t squared anytime something's thrown up or launched into the air and then comes back down. Then the next number, the initial velocity, we had 70 feet per second. And then our initial height. Since this was launched from ground level, that would be a plus 0. And in math, we don't write plus zeros. So we're not going to leave that in there. All right, next thing I would do is I'd talk about where the interval is. What is our interval? And in this case, we're talking about from 1 second to 3 seconds. So we've launched this little toy rocket up into the air, probably 5 or 6 seconds before it comes back to the ground. I'd like to know, how fast is it going between seconds 1 and 3? Not at the beginning. We know how fast it's going at the beginning. But how fast is it going on average between seconds 1 and 3? All right, so let's fill in the numbers into this formula. So velocity average equals, well, first off, we want S of the t2 number. So we want the value of this function when the time is 3 minus the S of 1 number, the value of the function when time is 1. All divided by the second time, 3 seconds, minus the first time, 1 second. That's essentially the same as h from the quotient, difference quotient the other day. That's going to be an obvious one. That's 2. Now for the other ones, what you're doing is you're first going to plug a 3 into the equation where the t is, and if you do that, you'll get 66. Again, you have a calculator, you can do this. And then the next thing we're going to do is we're going to plug a 1 into that same location, and we're going to minus those answers. When I plug a 1 into that same location for t, I get 54. All right, now I'm going to minus those answers. 66 minus 54 is 12. Then I'm going to divide by 2. So there's my numerical answer, but it's a word problem, so it's got to have word answers. So the final answer then would be 6, and then the unit of measurement we were using for our speed would be feet per second. So if it had an initial velocity of 70 feet per second, But between times 1 and 3, the new velocity was 6 feet per second, the average. You can see that this thing is definitely slowing down. And that's what gravity does. It slows things down, pulls them back. All right, so your work today is very similar to this. We'll be working on this topic for a couple of days. So if you have questions, feel free to ask today, or you can ask tomorrow if you're home and you're going to be back in class tomorrow. All right, good luck.